General stuff.
Professor Dave, let's learn about absolute values.
He knows a lot about all kinds of stuff. Professor Dave explains.
In our haste to get through algebra, there's one topic we didn't mention. So before we move on, let's quickly cover absolute values. It's important to know what these are and how to graph them. So let's become familiar with this definition. The absolute value of any real number, x, which is denoted by these little bracket type things, is the distance from 0 to that number on a number. A number line. Take the number 3. This is 3 units away from 0, so the absolute value of 3 is 3. Now look at negative 3. This is also 3 units away from 0, so the absolute value of negative 3 is 3. That brings us to a more practical definition of absolute value as being the magnitude of a number disregarding its sign. Positive numbers are unchanged by taking the absolute value, while negative numbers simply drop the negative sign and become positive. This applies not just to integers, but all real numbers, whether rational or irrational. Absolute values obey properties just like other operations, so we can see that the absolute value of AB can be split up into the product of two absolute values, and the same goes for division. However, let's note that the absolute value of AB can be split up into the product of two absolute values, and the same goes for division. However, let's note that the absolute value of A plus B does not equal the absolute value of A plus the absolute value of B, which we can demonstrate with the values 1 and negative 1. We clearly don't get the same thing. When we encounter 1, we clearly don't get the same thing. When we encounter absolute values while solving equations, it just adds another step. If we have the absolute value of x equals 2, that means x could be 2 or negative 2, so there are two solutions to this equation. If we try a trickier one, like the absolute value of 2x minus 1 equals 5, then again, we split this up into two equations. It could either be the case that 2x minus 1 equals 5, or 2x minus 1 could equal negative 5, because once we take the absolute value, we get 5 either way. That means we now have to solve both of these equations to get the two possible values of x. For the first one, we add 1, divide by 2, and x equals 3. For the other, we do the same thing, but we get x equals negative 2. So those are the two solutions in this case. The equations can get harder than this, but the approach will always be the same. The last thing we want to do is look at simple graphs with absolute values. We know that a graph of y equals x will look like this. The x and y values at every single point are equal to one another, and it's just a line with a slope of 1 and a y-intercept of 0. Now, what if we want to graph y equals the absolute value of x? Well, as we said, all positive values remain unchanged, so everything from the y-axis to the right will be just like it is now. But negative values will have their signs reversed. When we plug in -1 for x, we don't get -1 for y, we get +1. -2 gives us +2, and so forth. That means that everything to the left of the y-axis, or all the negative inputs for x, will be reflected across the x-axis, so that we get the positive versions of all these y values, resulting in this V-shaped graph rather than the line we had before. This can be transformed in all kinds of ways that we will learn later. For now, we just want to understand some basics about absolute values, what they are, and what they do. With that covered, let's check comprehension. If we try a trickier one, like the absolute value of 2x minus 1 equals 5, then again, we split this up into two equations. It could either be the case that 2x minus 1 equals 5, or 2x minus 1 could equal -5, because once we take the absolute value, we get 5 either way. That means we now have to solve both plug in the big 5, then again, we split this up into two equations. It could either be the case that 2x minus 1 equals 5, or 2x minus 1 could equal negative 5, because once we take the absolute value, we get 5 either way. That means we now have to solve both of these equations to get the two possible values of x. For the first one, we add 1, divide by 2, and x equals 3. For the other, we do the same thing, but we get x equals negative 2. So those are the two solutions in this case. The equations can get harder than this, but the approach will always be the same. The last thing we want to do is look at simple graphs with absolute. Now, what if we said all positive values, and we plot that means other than the line we had that we about absolute. Let's check comprehension. It's Professor Dave. I want to tell you about the types of numbers.
He knows a lot about all kinds of stuff. Professor Dave explains.
We have already begun to look at some different types of numbers, but it is time to do a survey of all the types of numbers that exist and make sure we understand their characteristics. To do this, we can look at the taxonomy of numbers, just like we would look at the taxonomy of biological organisms or fundamental particles. We start at the top with all numbers. Any number you can possibly conceive of, they are all here somewhere. But some numbers are real, while some numbers are imaginary. Real numbers are probably still all the ones you were thinking of, so let's define imaginary numbers. Remember when we said that we can't take the square root of a negative number? In a certain sense, you can't, because there is no number that when squared will produce a negative number. However, in another sense, we can take the square root of a negative number if we admit that the result is imaginary. While the square root of 1 is simply 1, we will say that the square root of negative 1 is I. This is a lowercase I, always in italics, and it is the fundamental imaginary number. The square root of negative 4 would be 2i, because negative 4 is equal to 4 times negative 1. So this radical could be split up into root 4 times root negative 1, which is therefore 2 times I, or 2i. That covers imaginary numbers, so let's go back to the real numbers. Within the category of real numbers, there are two subcategories, rational and irrational. Rational numbers are defined as any number that can be expressed as the ratio of two integers. 3/2, 93/604. You just make a fraction, put any integer on top and any integer on the bottom, and you've got a rational number. The number on the bottom can also be 1, so all the integers themselves qualify as rational numbers. The only number that can't go on the bottom is 0, as that will yield a value that is undefined. Now, what are these irrational numbers? Given the definition of a rational number, clearly an irrational number is one that can't be expressed as the ratio of two integers. But what could these numbers be? Irrational numbers are ones that have non-repeating decimals that are non-terminating, meaning they continue forever with no pattern. The square root of 2 is such a number. If we plug this into a calculator, it will tell us that the answer is 1.4142, etc., etc., but no matter how many digits your calculator displays, it's not giving you the full story. This number extends forever, which means we can never list the square root of 2 as a decimal and be infinitely accurate, the way we can with 3/2. 3/2, or 1.5, is exactly 3 over exactly 2. If we try to approximate root 2 this way, we can get very close with something like 665,857 over 470,832. But it's not exactly right, and when we square this number, we get something just ever so slightly larger than 2. No matter how precise you try to get with this ratio, you will never quite get to the true value. Now, you might be wondering, if we can't write out this number, no matter what we do, doesn't that make this number imaginary? The answer is no. Nature is very clear in communicating to us that numbers like root 2 do indeed exist. If you make a right triangle that has legs with a length of 1, the third side will have a length of root 2. This triangle exists, so root 2 exists. It is a real number. It is simply irrational. When it was discovered by the ancient Greeks that irrational numbers must exist, all hell broke loose as it threatened the mystical notion that the world of numbers must obey a divine perfection. Other irrational numbers include pi, which is the ratio of the circumference of a circle to its diameter. We all probably know the first few digits of pi, which are 3.14159 yada yada yada. Again, this number never ends, with no pattern whatsoever in the digits. And it's not for lack of trying. Mathematicians have checked. With computers, we can calculate pi out to literally trillions of decimal places, and the numbers are random throughout. Once again, even though pi is irrational, it is a real number because circles are real, and all circles have a circumference. But we will get to triangles and circles when we start looking at geometry right after this. Let's quickly mention that there are numbers with non-terminating decimals that are actually rational. Take, for example, 1/3. If we convert this to a decimal, we get 0.3, with the 3 repeating forever. Although the 3's go forever, this is a pattern. It's 3, then 3, then 3, and so forth. When decimals extend forever, but in a pattern like this, they are actually rational, because they can indeed be expressed as the ratio of two integers, in this case 1/3. Another example would be 1/9, or 0.1 repeating. That's what this little bar means. Whatever is under the bar repeats forever. In this case, just the number 1. 2/9 is equal to 0.2 repeating. And this continues all the way up to 9/9. That would be 0.9 repeating. And this is absolutely equivalent to 1. To prove this, we can rationalize that if the 9's extend forever, then there cannot be any number in between this number and 1, and they therefore must be the same number. There are other numbers with non-terminating decimals in a pattern of 2 or 3 repeating digits, or more. These are all rational numbers that are simply the decimal versions of some fraction. If we want to, we can subdivide rational numbers further to describe types of numbers we already know about, like fractions and integers. Fractions are all the numbers that happen in between the integers, and there are infinitely many of them in between each integer. Within integers, we can describe whole numbers, which are all the integers starting from 0 and going in the positive direction, and natural numbers, which are all the integers starting from 1, so the same as whole numbers, just without the 0. And that's pretty much all we need. After all this, we should be able to describe the difference between real and imaginary numbers, and within the real numbers, the difference between rational and irrational numbers. To make sure that's the case, let's check comprehension. Hey, it's Professor Dave. Let's learn about geometry.
He knows a lot about all kinds of stuff. Professor Dave explains.
If you could go back and visit any time in the history of mankind, which would it be? The Roaring '20s? The Renaissance? Those are some pretty good ones, no doubt, but my pick would definitely be ancient Greece. This civilization produced some of the most astounding leaps of intellect in the history of our species. In this era, early society truly evolved into a form that held the triumphs of the mind in highest regard. And as a result, the Greeks revolutionized philosophy, government, and you guessed it, mathematics. While there were many important figures in these fields, some of the best work in math was done by a fellow named Pythagoras. His work influenced great thinkers like Plato, and therefore all of Western civilization. This early branch of mathematics, now called geometry, was derived largely from drawing pictures in the sand, and it is one of the oldest topics in math. Great thinkers would draw shapes like circles, rectangles, and triangles, and try to understand the characteristics of these perfect forms. In this way, mathematics came to be defined as the field of inquiry in which all questions have completely objective answers. The sum of two angles, the ratio of side lengths on a triangle, these are values that can be firmly arrived at and are completely inarguable, just like the solutions of polynomials that we studied in basic algebra. This kind of certainty was impossible in the crude physical world, the mysterious subject of natural philosophy. Mathematics was revered as the study of divine perfection in physical form, and Pythagoras even had a little bit of a club surrounding his beliefs about numbers. Or we can go ahead and say it was a cult, but a nice math form. And Pythagoras even had a little bit of a club surrounding his beliefs about numbers. Or we can go ahead and say it was a cult, but a nice math cult. Its members were called Pythagoreans, and among their doctrines was a healthy dash of mysticism for good measure. Some of it turned out to be nonsense, of course, like their belief that the orbits of celestial bodies must obey perfect numerical ratios, just like the consonant musical intervals. As it turned out, this space symphony, as romantic as it sounds, is not real. The planets are distributed about the solar system more or less at random, just like every other planetary system we can see in our galaxy. But their contributions to math have stuck around, and between the work of Pythagoras and other great mathematicians like Euclid, mankind's ability to describe the universe was dramatically transformed. This change was so profound, in fact, that the geometry we learn in high school today is not very different from the geometry of this ancient time. So let's move forward and learn all about the shapes and angles and axioms that comprise the topic of geometry. And angles and axioms that comprise the topic of geometry. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me. Professor Dave here. Let's talk about points, lines, and planes.
He knows a lot about all kinds of stuff. Professor Dave explains.
As we just discussed, geometry was developed in ancient Greece, and when we learn the geometry of this time, we refer to it as Euclidean geometry, in reference to the mathematician Euclid, to whom it is attributed. His work, which built upon the work of earlier mathematicians like Pythagoras, describes a set of axioms and postulates from which a variety of theorems can be derived. Let's learn about the physical constructs that these axioms describe, so that we can learn about all the math we can do with them. First, we look at a point. This is nothing more than a location in space. It is zero-dimensional, meaning that it has no dimensions of any kind. We represent points with little dots and some capital letter, making sure to realize that the dot we draw is infinitely larger than the point it is meant to represent. From here, we can construct a one-dimensional object by stringing an infinite number of points along a particular dimension. This object is called a line. Points and lines are familiar to us from algebra, but now let's examine a two-dimensional object. This can be achieved by stringing an infinite number of lines along a dimension perpendicular to the line. This is called a plane. And then, if we string an infinite number of planes in either direction, we get three-dimensional space. Point, line, plane, space. 0, 1, 2, and 3 dimensions. Another linearity we can identify is that a point is just a point, but any 2 points can define a line, since there is only one line that contains both of these points. Extrapolating further, any 3 points that aren't all collinear can define a plane, since there is only one plane that contains all 3 of these points. We should mention that these figures are idealized concepts. We can never create a plane that is infinitely thin so as to legitimately consist of only 2 spatial dimensions. Even a piece of paper has some thickness, even if it's hard to see with the human eye. But we can create mental idealizations of these objects and discuss them concretely, and the conclusions we draw from them will have application in the physical world, where we can approximate certain systems as being perfectly Euclidean. Just to list a bit more terminology, while a line extends infinitely along its one dimension in both directions, if we chop one end off, giving it a definite starting point, we call this a ray. If we chop off both ends, leaving some chunk left over in the middle, this is called a line segment. Line segments have 2 endpoints. Rays have 1 endpoint, and lines have none. We can use lines, rays, and line segment to generate all kinds of figures. We can make shapes with differing numbers of sides, and we can also create all kinds of angles between these lines. There is kinds of angles between these lines. There is plenty to discuss regarding the types of angles that are possible, their magnitudes, and their relationships. So let's move on and talk about angles. Thanks for watching, guys. Subscribe to my channel for more tutorials. It's Professor Dave. Let's discuss angles.
He knows a lot about all kinds of stuff. Professor Dave explains.
Now we know what lines are, so let's draw a few. Here are 2 lines, and they cross at this point. But in what way do they cross? Do they approach one another slowly and then diverge slowly, or is it more rapid? In asking this question, we are asking about the angle between the lines. If a door is closed, it's just closed. But if it's open, how open is it? Is it slightly ajar? Is it wide open? The angle between the door and the wall simply represents a way of reporting how open the door is without having to make any reference to any spatial dimensions. Angles are measurements that are independent of the dimensions of objects, and they are ubiquitous in our everyday life. To begin examining angles, we can just look at 2 rays that start at the same point, which we can call the vertex, and the distance between the rays, denoted by this curved line segment, is an angle. Moving these rays closer together and further apart, while their endpoints are anchored together, will generate different angles. While there are a few ways to measure angles, we will first learn how to use degrees. There are 360 degrees in a circle, so we can take this tiny angle, watch it increase up to 90 degrees, and then continue all the way until 180, at which point we just have a line. If we continue in this direction, it will then go down from 180 all the way back to 0, since the angle will be getting smaller just on the other side. Let's learn about some types of angles. If an angle is less than 90 degrees, it's called an acute angle. We can remember this because an acute angle is cute and tiny. If an angle is exactly 90 degrees, this is a right angle, and this will be denoted by a square. If the angle is between 90 and 180 degrees, this is called an obtuse angle. So we should now be able to look at any angle and label it as acute, right, or obtuse. Now instead of two rays, let's use two lines. If these lines cross, we generate four angles. What are the relationships of these angles? First, we can examine the angles that are directly opposite one another, like these two. These are called vertical angles, and they are always equal to one another. This seems intuitive by looking at the diagram, but geometry is all about rigorously proving things that might seem obvious, though we don't know why. We also have adjacent angles, which are the ones that are next to each other. And if these are the result of two lines crossing like this, these are also called supplementary. We can also have complementary angles, which add up to 90 degrees. With these rules alone, we should be able to look at a diagram like this with some unknown angles and solve for the unknown angles on the basis of these rules. Let's also recall some relationships between lines. If two lines within a plane intersect at a right angle, they are called perpendicular lines. If two lines within a plane do not intersect, they are called parallel lines. If we draw two parallel lines and then a third line that crosses both of them, we can define some more terms. These four angles on the inside are called interior angles. These four angles on the outside are called exterior angles. Because of the relationships between vertical angles and supplemental angles, we can see that there are two sets of four equivalent angles here. First, each angle is equal to the one across from it. Then, these angles here are called alternate interior angles, and if these lines are parallel, they must be equal. The same goes for these alternate exterior angles. They must also be equal. This is stated by the alternate interior angles theorem and the alternate exterior angles theorem. There is also the same side interior angles theorem, which tells us that interior angles on the same side of the transversal are supplementary. That makes sense because these are supplementary and this one is equal to this one. So these two must also add up to 180. Lastly, angles in the same position with respect to one another are called corresponding angles. We will see diagrams like this quite a lot in geometry, and we may even have to do algebra with them. Like if we set these complementary angles equal to 3x x and x plus 10. How do we find the measure of these angles? angles. We just use the definition of complementary angles. They must add up to 90 degrees, so we make an equation, combine like terms to get 4x plus 10 equals 90, subtract 10, and divide by 4, which gives us 20 degrees for x. Plugging in 20, that makes the angles 30 and 60 degrees. Now that we've worked a bit with lines, it's time to look at shapes, which each have some number of line segments for sides. If we are talking about straight lines, we can't have a shape with one line segment, nor two. So it would seem that 3 line segments are the minimum required to produce a shape. And this simplest shape is called a triangle. Let's move forward and learn about all different kinds of triangles. But first, let's check comprehension. Thanks for watching. Professor Dave here. Let's learn about different types of triangles.
He knows a lot about all kinds of stuff. Professor Dave explains.
We know that if we connect three line segments, we can create a simple shape called a triangle. But in what way will these lines connect? And what are the different types of triangles that will result? Let's go through a list of the most common types of triangles now. First, a few general definitions. Since we know what acute, obtuse, and right angles are, we can then learn about acute, obtuse, and right triangles. Acute triangles have angles that are all acute, or less than 90 degrees. An obtuse triangle has one obtuse angle, or more than 90 degrees. And a right triangle has one right angle. As we can see by looking at the angles in these triangles and every other triangle we could possibly draw, the angles in a triangle will always add up to 180 degrees. This is why any triangle can have at most one right or obtuse angle, because two of them would add up to 180 or more, and then there is nothing left for the third angle. This fact will help us algebraically determine the measures of certain angles later. Triangles can be classified not just by angles, but also by side lengths. A scalene triangle is defined as having three sides of different lengths. An isosceles triangle has two sides out of the three that are exactly the same length, and therefore two angles that are precisely the same measure, specifically the two angles that are opposite the two identical sides. And an equilateral triangle has all three sides of the same length, and therefore three identical angles. Since the three identical angles must add up to 180 degrees, each angle must therefore be 60 degrees in an equilateral triangle. Every triangle must be one of these three types, because if they have three sides, it must either be the case that they are all the same, two are the same, or none are the same, as those are all the options we have. It's worth our time to also quickly mention some special kinds of right triangles. One is the 45-45-90 triangle. This will have two legs of equal length x, and a third side, a hypotenuse, of length x root 2. There are also 30-60-90 triangles, and these have sides of length x, x root 3, and 2x. Now that we are equipped with all of this information, we should be able to look at a diagram like this and fill in all the missing angles. We just fill them in one at a time by using the rules we know. If we have one of two vertical angles, the other will be the same as the first. If we have two angles in a triangle, then the third will be 180 minus the other two. If we have one of two adjacent angles, the other will be 180 minus the first, as these are supplementary, such as with the case of an exterior angle like this one. The exterior angle will also be equal to the sum of the other two angles in the triangle, since this one plus the exterior angle equals 180, and this one plus the other two also equals 180. So these values must be equal. This kind of reasoning is the essence of geometry. All we are really doing is drawing pictures in the sand, like the Greeks did, and asking questions about them. What can and can't be true about these shapes? It's like a playground for the brain, and if we follow the rules of the playground, we get meaningful answers to questions. These kinds of rules, like the ones that dictate angle relationships, will be applied constantly during our study of geometry. So let's check comprehension. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. It's Professor Dave. Let's compare triangles.
He knows a lot about all kinds of stuff. Professor Dave explains.
In geometry, we are sometimes concerned with proving things. Unlike the real world, where nothing could ever be proven, only shown to be consistent beyond reasonable doubt, in the perfect realm of mathematics, things can indeed be proven to be inarguably true, and our construction of proofs, as meticulous as they may seem, are incredible demonstrations of logic. One of the things we will want to prove is the relationship between two shapes, like two triangles. Two triangles might be unrelated, or they may have some special relationship. They could be similar, meaning they have precisely the same shape, just different sizes, or they could be congruent, meaning they are absolutely identical. When trying to demonstrate similarity, we have to look at the corresponding sides and angles. Here are two triangles that look like they might be similar. We can prove they are similar if the corresponding sides have lengths that are proportional, or if the corresponding angles are identical. This means that if this triangle has sides equal to 2, 4, and 6, while this one has
Very simple, Dave.